Hello everybody. In this episode, I'll be speaking with Lee Sharkey. Lee is an interpretability researcher at Goodfire. He co-founded Apollo Research, which he recently left, and he's most well known for his early work on sparse autoencoders. Links to what we're speaking about are available in the description. There's a transcript available at axrp.net. You can tell me what you think about this episode at axrp.fyi. That's axrp.fyi. And you can become a patron at patreon.com/axrpodcast. Well, let's continue to the episode. Well, Lee, welcome to AXRP.
It's great to be here.
Yeah, so today we're going to talk about this paper, Interpretability in Parameter Space, Minimizing Mechanistic Description Length with Attribution-based Parameter Decomposition. It's authored by Dan Brown, Lucius Buschnock, Stefan Heimersheim, those three being, I guess, joint first authors, Jake Mendel, and yourself. So I guess how would you summarize just what's this paper doing?
Yeah, so I would say that this paper was born out of two lines of thinking. One primarily, coming from what I was thinking about, and one coming from where Lucius was thinking about. And where I was coming from was, we'd been working with SAEs, sparse autoencoders, for some time. The community got quite excited about them. And we'd just been, thinking about them quite a lot and noticing just a bunch of conceptual and ultimately practical issues with them. And then, the line of thinking that Lucius had been thinking about was thinking about just, a potential area of research that might form, a foundation for decomposing neural networks. And what this paper does is basically bring those lines of thinking together. And the whole thing that we're trying to achieve here is just breaking up the parameters of the network instead of its activations.
Fair enough. So yeah, I guess the hope is to when you say break up the parameters of the network, if I look at the paper, there you have this APD method, and it seems like there's the core of it is this objective of here's how we're going to decompose the network. There are these three parts of the objective. Can you walk us through just what those are?
Yeah. So as I mentioned, the whole goal here is to break up the parameters of a network into different components. So and this is necessary for understanding what the objective of this algorithm is. So we have a neural network, and as many of these networks are, they're composed of matrices, and these matrices are the parameters of the network. And even though these are matrices, you can flatten these matrices out and just concatenate them all together, and you just make one big vector that you call your parameter vector. And this is your neural network lives as a vector in parameter space.
Yep.
And what the method does is it basically supposes that you can break up the neural network into a bunch of mechanisms, and those mechanisms sum together to the parameters of the original network. And so what we want to do then is we want to start with a set of parameter vectors that all sum to the initially they sum to a random vector because they're randomly initialized. But we basically want to optimize these parameter components, these the components of this sum and we want to sum to the original network. And we optimize them such that they do actually in fact sum to the parameters of the original network. 2, that as few as possible of them are used on any given forward pass. And 3, that they are in some sense simple, that individually they don't use very much computational machinery, because one of the ways that you might have a set of parameter vectors that sums to the parameters of the original model is just to have one parameter vector that is in fact the parameters of the original network, and as few as possible of these are used in any given forward pass, because that's just it just uses one of these parameter vectors,
Hmm.
but it's not very simple, right? You haven't really done very much work to decompose this into smaller steps that you might more easily be able to understand. And so you want these individual parameter components to be simple as well, as faithful to the original network, that is BSM, and also minimal, as few as possible of them are necessary on any given forward pass.
Gotcha. So one thing that I guess immediately struck me about this idea is like, so it's sort of it's sort of presented as like, SAEs have these problems, and so we're gonna do this thing. And it strikes me as almost just like a sparse autoencoder for the network, right? Like what's a sparse autoencoder? Well, you want to like, you have this like activation layer, and you want to, have something that recreates the activation layer, and you want it to like sparsely activate, there are a bunch of components, they should sparsely activate on any given like thing. And, if you train it with like L1 loss or L2 loss or something, like somehow you're supporting simplicity as well. How I'm wondering, like, how much do you think there is to this analogy?
I do think there are many parallels for sure. I wouldn't want to overstate them because, I do feel like much more satisfied with the APD direction, and so, but as you point out, there are many similarities. You might think of SAEs as, in some sense, minimizing the description length of a given set of activations. You want to be able to, be able to describe in as few bits as possible a given data set of activations in a given layer. But the method basically, I don't know. It focuses on a slightly different object. It focuses on parameter space rather than activation space.
Right.
And in that sense, kind of focuses more on the computations rather than the results of the computations. But there is, it's not a coincidence that we've been thinking about SAEs for some time, and then we come up with this direction. There are some deeper similarities there, but I think the core similarity is that whenever you're describing a neural network, you in some sense want to use as few objects as possible, because in that way you're going to be able to break it up into individually more understandable or simpler chunks. And the hope then is that you can if you understand those chunks, you can understand the rest of the network as well. And so both of them rely on that principle, but act on different objects and a few other differences as well.
Sure. So I think just to get people to understand like what APD is, I think it's actually helpful to sort of go through the three parts of the objective and talk through them. So
yep.
I guess the first part is you have these like this set of vectors in parameter space, and they have to sum up together to make the whole network.
Yep.
I think the first thing that strikes that might strike, or at least it struck me as somewhat strange, is because you're looking at vectors in parameter space rather than like subsets of the parameters of the neural network. You're allowed to say like, oh yeah, this mechanism is 3 times this parameter minus 2 times this parameter plus half of this other parameter. Like at first blush, it seems like there's something kind of strange about that. And I'm wondering, like, is this, well, firstly, are there like other parts of the objective that like mitigate against this sort of thing? Or if there aren't, like, is this just the thing that ought to be done?
I'm inclined to say that implicitly there are, that I think what we will find is that, and we do, to some extent find this in some of our experiments, that even though networks try not, we don't want our understanding of a neural network to be in some sense privilege some basis either in activation space or in parameter space. The network doesn't necessarily have a fundamental we don't get to presume a fundamental basis. We have to go and find that basis either in activation space or parameter space. However, you might be familiar with the idea of just privileged bases. This is the idea that because of the activation functions serving as these non-linearities, certain bases might be preferred. And in particular, bases that somewhat align with neurons, although not equivalent to the unit basis in the neuron basis. So it does feel likely to be the case that because neural networks they seem to have some tendency to align with the neuron bases under some data distributions and some training objectives. I would guess then that APD, if those bases are indeed privileged in the network, APD should be able to recover them, and thus implicitly kind of has a bias toward, if it has a bias toward finding true things in the network, and the network has some it privileges some bases, then it should ultimately find that. But I'm not sure if it does have a part of the objective that biases it toward that explicitly.
Fair enough. So I guess the next thing I want to talk about that's I guess somewhat distinct to the method is the second part of optimizing for minimality. So concretely, like, how does this work? What are you actually optimizing for here?
Yeah, so we came up with a couple of different ways that you might be able to do this, and we use one in particular that is we call it the top K method. So we have these set of parameter components that we're training, and we want them to each individually take the form of one individual mechanism of the network. And the way we want these mechanisms to have the properties such that as few as possible of them are necessary on a given forward pass. And so the way we optimize for this then is that we have two forward passes and two backward passes. So on the first forward pass, we use the sum parameter components, which are approximately equivalent to the parameters of the original network. And then on the first backward pass, we take the gradients of each of the output dimensions with respect to the parameters. And the idea here is that we use these gradients as attributions of which of these parameter components was most influential over the output.
Okay.
And so in some sense, which of these parameter components is most causally responsible for the output.
Okay.
And then on the so we take those attributions. Each parameter component has a number that is some approximation of how important it was for the output.
And is that just is that number just the sum of the absolute values of all the attributions, or?
It's a slightly more complicated formula. We basically you take some inner product with the parameter components themselves and the gradients, but you can conceptually approximate it with that. It's roughly that idea.
Sure.
And so you basically you have this number that tells you approximately how important this parameter component was for the output, and then you say, well, I'm going to only take the top K most important parameter components, and then you do a second forward pass only using the top K most important parameter components. And what this should do whenever you train the output of that second forward pass to be the same as the original model is that it should update these active parameter components such that they become more important on this forward pass for that data point. So they basically should increase their attributions on this data point compared with before the gradient update. And the gradient update is just the second backward pass. So that's basically what the 4 steps of that training step do. Gotcha.
So it's, I guess my main question is, it seems like the fundamental thing here is minimizing the number, not the number of mechanisms total, but the number of mechanisms that are relevant for any one for any like single forward pass of the network. I think when I first came across this idea, it just like wasn't at all intuitive to me why that should be the minimality that's necessary, rather than just like minimizing the total number. What's going on there?
Yeah. So I'm just trying to understand what the confusion is. So I think the way maybe to think about it is that if I wanted to minimize just the number of parameter components that I used on any given forward pass, one thing I might do is just as we were discussing earlier, we may just use the parameters of the original network. Of course, this doesn't really this isn't satisfactory because it doesn't break up the parameter components into something that is simpler than the original network. And so one thing that you might so already we don't get to just minimize the number of parameter components that are active on a given forward pass. So you might then imagine that there is like a Pareto frontier of how many parameter components I've split up the network into versus how simple they are.
Yeah.
And there's going to be some, for a given level of simplicity, I'm going to require a certain number of parameter components on a given forward pass. But yeah, you don't really get to, I guess, I don't know. Yeah, maybe you can spell the confusion a bit more.
Basically, my question is, so in actual APD, right? One of the things you're optimizing for is that on any given forward pass, there should be few components active. But like on different forward paths, like maybe you have passes. Maybe on this forward pass you have mechanisms like 1, 3, and 5 active. On this forward pass you have mechanisms 2, 4, and 6 active. And then you're like, this is like pretty good, But you can imagine a world where you say like, hey, I just want there to be as few mechanisms as possible just for all the inputs, right?
Yeah.
So in this hypothetical network where like, you have like 1, 3, and 5 on this input, 2, 4, and 6 on this input. For APD, you're saying like, oh yeah, that's like, it's only using 3 mechanisms for any forward pass. But you could have a hypothetical method that's saying, that's like 6 mechanisms that are being used in total, and I want to like minimize that number. So why is it like the per forward pass number that we want to minimize?
Yeah, I think it is in fact the other one that you want to minimize. You do want to minimize the total number, because we're ultimately averaging the gradient steps over batches such that it will on average point toward a configuration such that that if you get to share parameter components between these different data points, if you have a data point that has 1, 3, and 5 and another one that has 1, 4, and 6. This one should be favored over the one where you just get to split up one into 2 different mechanisms that is active on both of these data points. I guess what I'm saying is that you arrive at a case. You basically do want to optimize for cases where things are shared, and thus kind of where there is as few mechanisms as possible over the entire data set. You just happen to be doing this, batch-wise over individual data points.
My understanding of the method is, so you have this like batch of inputs, right? And what you do is, in a batched way, you like for each input you take the top k. You do batch top k, but like that's
sure.
Sort of an implementation detail, right?
Yep.
So for each of these inputs, you take the top k mechanisms that are being used.
Yeah.
And then you upweight, and then you like do a backward pass where you're optimizing for, on each input, the top k things that were used for that input are basically optimized to better reconstruct the output of the network on that particular input.
Sure.
And so I don't see mechanistically like you know, if I have the like 135.246 case, right? I don't see like how that's going to be optimized for like, no, actually you should like use the same few things, because like for like you're just taking the top k for both of them, right? You're not like I don't see where the gradient term would be for things to share mechanisms. Like in the 135.246 case, I think you just like upweight 135 on the first input and upweight 246 on the second input, right?
Yeah, I guess maybe it might be useful to think of a concrete example. So maybe the toy model of superposition model might be a useful example here. So suppose the toy model of superposition is a model developed at Anthropic. It's a very simple model where there are sparsely activating input features, and these, just a few of these are active on any given input, and the model consists of, it's also just a very simple model. It's got a weight matrix, and that weight matrix has as many suppose it has as many rows as the number of sparsely active input features, and it has as many it has this basically smaller number of columns. So it's basically like a down projection matrix from data space into this hidden space. And so, and then this down projection gets up projected by this matrix whenever you like you could use in theory a different matrix, but you can just transpose the matrix, and that spits out an output after you pass it through a ReLU activation, and you basically want to reconstruct the input data. And there's a bias in there. Just so what? Suppose then you have some input datum which has the first and the third and the fifth features active. So these are active. These are in fact active inputs. But in the in APD, you don't necessarily get to. You haven't yet learned whether or not there is your parameter components haven't yet learned to correspond to these input features. So you might then have a bunch of basically, I guess maybe one thing then to think about is, well, suppose you have a bunch of different parameter components. Because they're not aligned with the features in some sense, there's too many of these parameter components active, and you want to APD is designed to learn only as many parameter components as are necessary to explain the whatever the network is doing for on this data distribution. And you basically don't want it to learn more parameter components than are necessary, and this is what you achieve by both optimizing for minimality, such that as few as possible are necessary, and that they are as simple as possible. And so suppose you have two parameter components where even though the ground truth feature 1 is active, you have two of your parameter components are in fact active. One is maybe slightly more active than the other. But you don't want this, because like ultimately you want to learn only one of these parameter components per input feature. And the idea then is that in some of these cases where this input feature is active, and one of these parameter components is more active than the other, because it would be statistically unlikely that they are equally active. There will be cases where, because you're thresholding this, the one that does get active will get updated such that it in future cases like this where the feature 1 is active, it gets more attribution versus cases where it doesn't. Now, I'm not sure if this fully addresses your concern, but I think maybe one of the I guess I'm pointing at, if there is a ground truth where one thing is active and two things and two parameter components are then active, then this is something that we do, in fact, get to avoid by minimizing both for minimality, also for simplicity.
Right. So I think the image I am getting from your answer, which might be totally wrong, so tell me if it's wrong.
Sure.
But I think the thing you're saying is, okay, probably for every input, there are in fact like some parts of the network that are like, more active on that input. And like they're I think you're almost saying, like, imagine there is some ground truth decomposition that's like not super big, right? Well, if I have like input A and input B, right? And they in fact do use many of the same mechanisms, then it's going to be, then basically APD is going to be disincentivized from the like 135-246 solution, just because like, it's going to be, you're picking like few mechanisms active on any given thing, but you're trying to make it like mimic what the network actually does. And so if the thing the network is actually doing is, using some of the same like actual parts of the actual network, then you're going to push these like 246, to be close to the actual mechanisms of the actual network, and you're pushing 1, 2, and 3 to be close to the actual mechanisms of the actual network. So like they're just going to merge, basically.
Yeah.
Is that roughly right?
Yeah, I think so, yeah.
Okay. So in that case, like, yeah, so it seems like basically for this story to work, you're basically saying, no, there is some ground truth decomposition, and like, because we're doing this thing that's getting close to the ground truth decomposition, that's like what's powering our thing working, as opposed to some sort of constructivist thing of like, here's just the nicest way we can find of like decomposing things.
Yeah, this is a question I haven't quite made up my mind on yet. I think, in toy models, it can be the case that you have a ground truth decomposition because you made it that way. And the way that you might have designed this is that, if someone came to you and told you, well, I've got a equivalent way to describe this network that you designed yourself, and their description, uses more, it uses either more components than is necessary, or it uses more complex components than is necessary, then you might say, well, sure, kind of, but like, I think this other explanation, the one I used in my head to design this network, is better. And in some sense, then, it is more toward this like constructivist way of thinking. Maybe then, there is actually no such thing as a ground truth explanation for the network, even though you designed it, and even though you said this is the ground truth explanation. If there are other equivalent things where more objects, more complexity was necessary, then sure, there's still explanations, but they're not as good. And in the case of more natural networks, maybe it is also the case that even though we can debate whether or not there is some ground truth to the thing that the network is doing, the style of explanation that we most prefer is something that is the shortest, simplest explanation for what the network is doing.
So I think, but before we go further into the philosophy of APD, I think I want to just like get through the parts so that people fully understand. So the third kind of component of this objective function is simplicity. You're optimizing like each component to be simple. Can you tell us like what's simple?
Yeah. So the way we defined simple, simple is supposed to capture this intuitive notion that it uses as little computational machinery as possible. And what does it mean for a set of matrices to use as little computational machinery as possible? The definition that we settled on was that if the network consists of one matrix, that matrix is as low rank as possible. You can't get much simpler than a rank 1 matrix, and a rank 2 matrix is less simple. It does more things to a given input vector. And if your network consists of more matrices than just one, you basically get penalized for ranks in those matrices as well. So it's basically the thing that we want to minimize is the sum of the ranks over all of the matrices in a network. Now we are we're not fully happy with this, but we do think that this is like a fairly reasonable notion of what it means to use as little computational machinery as possible.
Yeah. So in some way, so if I think about what that's saying, right? Like saying that so there's something intuitive there, right? Like for instance, if you use fewer matrices, that should count as more simple. Like lower rank is basically saying like your matrix is secretly over like smaller dimensional input / smaller dimensional output space.
Yeah.
I think in some ways what it's saying is that like it's in some ways being basis independent in this kind of interesting sense, right? Like you're sort of saying that like the identity function versus like a weird like rotation and scaling, like as long as you're doing it on the same number of dimensions, like it's those counts as the same, which I think is actually plausible given that like different layers activations functions are like in some sense maybe they just should be incomparable in that way. Maybe you don't want to equate like these neurons with these neurons. I think like maybe the other thing that seems slightly strange about that is like by being basis independent, like by saying that the complexity of this weight matrix is just like the rank of it. Suppose you have like two components in one layer, right? By saying the complexity of both of them is the rank, somehow you're saying that like the basis you're thinking about for the computation of like thing A and the basis you're thinking about for the computation for the thing B are just like not related at all. And maybe there's something there that's worth. I don't exactly know what the objection there would be, but it seems like there's possibly something there that's worth getting into.
Yeah, I mean, I think this is. I think that's just something that we're willing to accept. We do want to basically, in some sense, what the exercise we're trying to do here is basically discretize the network into discrete objects. And ideally, we want to discretize it into objects that have as little to do with each other as possible.
Yeah.
And if it is the case, then that we can in fact just distinguish between one kind of operation and another. Sometimes that operation is used, and on other data points it is not. Then I think we're okay with that. But one of the reasons that APD was developed was the case of multidimensional features. And the idea of a multidimensional feature is that, well, maybe you don't get to just break things up into rank 1 components. Maybe you actually do in fact need more than one. So the classic example here is the days of the week features, where the days of the week lie on points in a circle, and
crucially they're in the right order, right?
And
because Monday, then
order.
Tuesday, then Wednesday.
Yeah, exactly.
Yeah.
And in order to describe these features, sure, you can describe them as 7 different directions in activation space, but you can more succinctly describe them as basically two-dimensional objects, basically. And if you want to, understand the understand the operations that are done on those, it might just be useful to think of them as 2 dimensions rather than 7 one-dimensional objects. The idea is that we want APD to be able to decompose networks into chunks that, if they do have these computational units that are best thought of as 2-dimensional rather than 1-dimensional, that it can indeed find those and isn't just decomposing things into too many objects.
Fair enough. So I guess I next want to just talk about like so I want to like test my intuitions for like, okay, basically do these objective functions make sense when I compare against, certain examples. So the first example I want to ask about is, suppose I have a decomposition of the network that's just like each component is one layer of the network.
Mhm.
Like component 1 is the first layer, component 2 is the second layer, component 3 is the third layer. Is that going to I feel like that might score well on APD, as long as like you're allowed like that many components, right? And so my reason for thinking this is basically you have the cost that each matrix is full rank, but unless there are like, I guess it's possible that there are like unused dimensions in the network that you could prune off, right? Like if there are some, like sometimes ReLU in ReLU networks, some neurons will die. So yeah, suppose you're like taking the weight matrices, but you're like pruning off the dead ReLUs, right? It seems like that might actually be optimal as long as you're allowed that many components, just because like it's a perfect recreation of the network and no other way of like mixing around the the things is going to save on like the total rank, because you just need that much rank total. Is that right?
It depends on the data distribution. There is a case where it is right, but it's a fairly strange case.
Okay.
Suppose you have a data distribution where for every input, all of your ReLUs in your 3 layers are always active. So fine, you've pruned off the dead ones. Those never activate, but on the other ones that do activate, they're always active. So everything is always above threshold. And so what you've really got here is just like 3 linear transformations.
Yep.
And in that case, you don't really get to summarize that any more than just describing the 3 linear transformations, because on every given input in our data distribution, there's always like some non-zero amount that each rank is used. Fine, there's going to be some infinitesimally small number of cases where it's perfectly orthogonal to some of the some of the smallest singular dimensions of some of these matrices, where and in that very small number of cases, that a parameter component that aligns with an activation that aligns with parameter components that align with that dimension, the attribution will be 0. But in almost every case, all of the ranks will be used. Now, you can imagine for certain other data distributions, well, I guess maybe one way to think about it is that wouldn't be a very useful neural network, because it's just doing the same transformation to every input, and that you might as well just use one linear transformation. The interesting thing about neural networks is that they can do different transformations to different inputs, and in that case, then in some inputs, you may use transformations that go one way, and on other inputs, you may use transformations that go another way.
Okay.
And that's the kind of thing that you want to be able to break up using APD.
Right. So sorry. If I think through this example, it seems like, suppose you have these alternate set of mechanisms, right? This alternate decomposition where like on this input, we're only using like, this half of the neurons, and on this input, we're only using like this half of the neurons.
Yeah.
At first, sorry, maybe tell me if I'm thinking about this wrong. It seems like this is actually a case where minimality per input is actually buying you something, because in my imagination, you're still using like the same amount of rank, and like maybe you still have the same total number of things, but the thing you're saving on is like in the per layer thing, like every layer is active on every input, right? Yeah. But like if you can break it up with like, this is only using a subset of the neurons, so I only need this subset of the mechanisms. Like, yeah, like is the thing it seems like maybe the thing I'm saving on there is like, maybe it's rank and maybe it's number of neurons, but like, number of components, but like on a per input basis rather than like over all the inputs.
Yeah, I think that's right. So, you might, suppose you have 2 components into each of these layers, and you've got 3 layers, and so you've got 6 components overall. Well, if your parameter components suppose your data distribution is split up such that you can in fact throw away half the network that is involved in one half of the data distribution, and you can, for the other half of the data distribution, throw away the other half of the network. So you can basically just treat these as two separate networks that happen to be mushed into one. And if so we've got these 6 parameter components, and if they're lined up such that one of these 3 of these parameter components they correspond to one of these data distributions, and the other 3 corresponds to the other data distribution, then yes, that on some inputs you'll be able to use only 3, and on others, in all cases you'll be able to use just 3. But if your parameter components don't line up perfectly with these distributions, you'll have to use 6 every time, which is just not something that you want to do if you want to decompose it into a smaller number of active objects at any given point.
Okay, so I think I feel satisfied with that case. I next want to just talk about so this is like a little bit out there, but to help me understand, I think it would be helpful for me to talk about doing APD to a car, right?
Go on.
So basically, because like a car is an instance where I feel like I understand what them. Well, okay, I'm not actually that good at cars, but I have a vague sense of like what they're like, and I think I have a vague sense of what the mechanisms in cars are, right? So if I imagine like taking a car and doing APD to it, right? I want some decomposition of all the like stuff in the car. That firstly, all the stuff in all of the decompositions just like reconstitutes the whole car. I'm not like leaving out a bit of the car. That makes sense to me.
Yep.
Secondly, I want there to be as few parts to my decomposition that are like relevant on any given like car situation. So so like there's some situation like maybe suppose we discretize time, right? And there's like some input to me driving, and then I do a thing, and then the car maybe it has to be a self-driving car for this to fully make sense.
Sure.
And then the third thing is that each component, the components have to be as simple as possible, right? One concern I have is, I think when people are driving a car, usually like there are a bunch of components that are active at the same time. That are basically always active at the same time, even though I think of them as different components. So one example I think is if you're like the steering wheel, right? There's always like an angle at which the steering wheel is going. And whenever the car is on, like that angle matters to how the car is going.
Sure.
There's also a speedometer, which like tells you how fast you're going, right? And that speedometer is always active whenever the thing is on. Now, if I imagine, like, would APD tell me that the steering wheel and the speedometer are the same, are part of the same component? I worry that it would, because there's no, I think there's no, like, complexity hit from describing, like if I describe them separately, that I have the complexity of the speedometer plus the complexity of the steering wheel. These two things, and if I describe them jointly as a speedometer and the steering wheel, then I've got to describe the speedometer, and I've got to describe the steering wheel, like same amount of complexity. But in the case where I merge them, I have like one component instead of 2. And like there's never like some cases where the steering wheel is active but the speedometer is not active, or vice versa. If I understand cars correctly, maybe people have a counterexample. So in this case, like, would APD tell me that the speedometer and the steering wheel are the same and are part of the same mechanism? And if so, is this a problem?
I think there's a kind of like, I don't know, functionalist stance that we're taking here, that like, we want to understand a particular function of the car, and I think it might help to specify what that function is. So suppose that function is just like, can I get me, a human, from A to B? And so suppose I live in a country that doesn't require speedometers, and I don't really care what my speed is, and it really just doesn't affect my behavior, and therefore it doesn't affect the behavior of the the car. In this case, we can basically ablate the speedometer, and the car would go from A to B with very little changed. Now, in a different context, whether or not this a speedometer might affect the decomposition that we think is like the most succinct description of the thing that is doing the driving from A to B. Another analogy here might be a more general case might be, well, we have the engine and we have the brakes. Now, whenever I'm moving, the brakes are not always on, and so whenever I don't need the brakes, whenever I'm not braking, I can basically ablate the brakes, and my the behavior of the car, the behavior of the Lee and car system is basically going to be unchanged. Now, of course, if I if I ablate the brakes and then do want them, there is a difference between those two worlds where I do have the brakes and I don't. There's like some sense in which breaking it up into thing that makes the car go forward and thing that makes the car go stop is actually a useful decomposition. So bringing it back to your example, I do think that it matters like the kind of function that we are specifying here. And in the case that you mentioned, it might not matter whether or not you decompose the car into the engine and the speedometer, because it's all one part of. In your example, there was no driver, and it's all part of one causal process. The speedometer is just basically intrinsically attached to the engine, and we can we therefore don't really get to chunk the system up into two different objects. But because the stance, what we're like describing as the function here, matters, that kind of determines whether or not you can in one sense ablate it and in another sense not. In one sense decompose them, and in another sense not.
Right. So I think so I mean, maybe one way of saying this is that like part of the like how do you tell that the speedometer and the steering wheel are different? Well, one way you can do it is you can have like sort of test cases, right? Where like you have this guy who like doesn't really care about how fast he's going, which is still a little bit weird, right? Because like at least back when I was driving, like that was relevant to like how how can you turn?
Sure.
But I don't know, maybe you can just figure that out by looking at the road and being smart, right?
Sure.
But like at the very least, you can go to a mechanic and you can like get your car in some sort of like test situation where like you're just like checking if the speedometer is accurate by like hooking it up to some like car treadmill thing, and like
sure
the steering wheel doesn't matter there, maybe or vice versa. So one way I could think about this is like this shows kind of the importance of like a diversity of like inputs for APD, that you've really got to look at the whole sort of relevant input space, and if you don't look at the whole relevant input space, you might inappropriately merge some mechanisms that like you could have distinguished. Is that maybe right, a takeaway?
That feels right. It does feel that it feels right that in order to just understand all the functions, we do need to look at all the kind of cases. In order to decompose networks into all the distinct mechanisms, we do need to look at all the cases where those mechanisms may be distinguishable. That feels like a reasonable takeaway. Yeah,
sure. I guess the next thing, actually, the other thing about the car that I thought about when you were talking about it seems relevant for just like identifying which mechanisms are active. So in the paper, the test for whether a mechanism is active is this like gradient-based attribution, right? Which is basically like, if you changed this bit of the network, would that result in a different output, right? Now, suppose I'm driving and I'm not using the brakes. If you change the brakes such that they were like always on, then that would change my driving behavior, right? Or like even in an incremental way, right? Like if you changed the brake pedal such that it was always like a little bit pressed, that would be slowing me down.
Yeah.
So am I right to think that if you use, and maybe we're just like straining the limits of analogy or whatever, but am I right to think that if we used the equivalent of like gradient-based attribution to decomposing a car, you would be thinking that the brakes were like always an active mechanism?
I think it may be like running up against the limits of the analogy, maybe, but one of the things that the gradient based attribution is supposed to approximate
Yep.
is if you were to what gradients are actually measuring is like if you twiddle the activations or the parameters in one direction,
Yep.
will it affect the thing with which you're taking the gradient off? So and the I don't know, this is supposed to approximate basically like how ablatable is this direction. You're basically saying if I moved, if I didn't just do a small twiddle, but like did a very large twiddle to, from where I currently am to 0, then should it affect the thing that I'm taking the gradient of? You're basically taking a first order approximation of the effect of ablating.
Yep.
That's just like what you're trying to do whenever you're taking the gradient here.
Yep.
And yeah, so maybe ablatability is like a way to port this into the analogy. Hence, like if you can ablate the brakes, you can and nothing changes in that situation, then the brakes are in some sense for this moment, the brakes are degenerate. The brakes just are not needed for this particular data point where I did not need to brake. But on data points where I was braking, I do not get to ablate the brakes and have that. The state does change quite a lot whether I ablate the brakes or not in cases where I am in fact requiring the brakes.
Fair enough. So I guess the last question that I want to ask, just to help me understand like ABD, is if I recall correctly in the either the abstract or the introduction of the paper, there's just this disclaimer that like, okay, parts of this are just like, implementation details, and like there's kind of a core idea, and there's like how you made it work for this paper, and like those are not like quite the same thing.
Yep. Out
of the stuff that we talked about, like, which parts do you feel like kind of the core important parts of like, the version of APD that you're interested in investigating, and which parts of it just felt like, okay, this is like the first way I thought of to operationalize this thing?
Certainly using gradient-based attributions is not something that we're wedded to at all. What they're supposed to do, as I mentioned, is just figure, it's supposed to get some measure of how causally important these, a given parameter component is. Now, it's not the only potential method that you might consider using. People have, you should be able to sub in any, method of causal attribution there and replace that. This is something that we're keen to replace, basically because gradient-based attributions will have all sorts of predictable pathologies, such as I mentioned that it's a first order approximation of causal ablation, but it is really just it's a first order approximation. It's not going to be very good. There will be cases where if you twiddle the parameters in a certain direction, and the output doesn't change very much, but in fact it is, if you blade the entire way, it does change. It does change a lot. A classic example of this is attention, where if you're really paying a lot of attention to a particular sequence position, your attention softmax is basically saturated in on that sequence position. And even if you change the parameters a fair bit, it may locally it may not change very much. But if you change them a lot, you may go from a regime where you were saturated to non-saturated, and then you realize in fact this was a causally important sequence position. And so there's just lots of predictable pathologies that will arise out of gradient-based attributions. we're also like not totally wedded to the definition of simplicity that we have. We're open to other potential definitions that may be more principled. For instance, one of the main motivations in the design process of this method was not to be basis privileged.
Yep.
And there are a bunch of reasons for this, but one of the reasons is that, well, representations or computations in neural networks seem to be distributed over a very large number of different things. The classic case is that you don't get to just look at an individual neuron and understand an individual function within the network by looking at one neuron. You have to at very least look at multiple neurons. Things seem to be distributed over multiple neurons, but it gets even worse than that. It's representations may be distributed across multiple layers. In fact, especially in residual networks, where you don't really get to just look at one layer to understand something. You have to look at multiple, and the same thing goes for attention heads. Maybe in fact. A lot of analysis looks at individual attention heads, but this is kind of an assumption. We're kind of assuming that the network has chunked it up such that one head does one thing. And
right.
There's some intuitive reasons to believe that, but there are some intuitive reasons to believe that one neuron does one thing, and there's no fundamental reason why it can't distribute things across attention heads. And there's some toy examples and some empirical evidence that this may be happening in networks. And so this is, there's a bunch of reasons why you might not want to be basis privileged. And the thing that our simplicity measure, it does in fact, privilege layers.
Yep.
Because it's the sum over layers. It doesn't, privilege particular ranks, but it does privilege layers. And we're open to versions of this metric that don't privilege layers. Aside from that, I think what we're the fundamental thing about this whole method is that we get to decompose parameters into directions in parameter space, and we're open to different ways to doing this. It's more. We hope this is just like a first pass of a general class of methods that do parameter decomposition, and the kind that we're introducing to some extent here is like linear parameter decomposition. We're decomposing it into something that sums to the parameters of the original network, and we think that's likely to be a somewhat powerful way to decompose networks. Not necessarily the only one. But we hope this points toward a broader class of networks that of which APD is just one.
Sure. Okay. It turns out I lied. I have another question just about how the method actually works, which is, so I don't know. I guess obviously there are a few hyperparameters in APD training, but one that feels very salient to me is like how many components actually get to be active on any given thing. So first of all, how in fact do you pick that?
It is one of the things that we want to move away from in future versions of the model. I mentioned that we were using an implementation that is like a top K implementation, where you're just choosing a certain value of K, and you're saying this is the number that is active on each data point. In fact, we used batch top K, where you're saying you get a little bit more flexibility per data point, but you still have to say over a batch of a given size, we still want on average there to be only K active per data point. And that's a hyperparameter that is like one of the main issues with the whole method is that it's currently like still pretty hyperparameter sensitive, and this is just one of the hyperparameters that if you manage to get rid of, then you may arrive at a more robust method. The way that we choose it is basically because we've got toy models, we have ground truth, and we can know whether or not the method is doing the right thing, and we can basically search for the right number of values of k such that it yields the ground truth mechanisms. But we want something that's more robust, such that if you didn't know the ground truth mechanisms, you could just choose an okay value for the hyperparameter, and you would be you could rest assured that you should end up with something approximately right.
Right. So one thing that occurs to me is so in the title it says like minimizing mechanistic description length with attribution-based parameter decomposition, and you present it as part of this minimizing minimal description length, like part of this family of things where you're trying to run some algorithm to describe stuff, and you want to minimize. It's related to all these ideas of Solomon induction and stuff. And I thought that one of the points of minimal description length type things was that it offered you this ability to have this principal choice of how to choose hyperparameters, right? Like, or at least these sorts of hyperparameters. Like I think of MDL as saying you could when you're doing regression, right? You can model it as degree 1 polynomial, or you can model it as a degree 2 or degree 3, and you have this trade-off between fit and something else, and MDL is supposed to tell you how many degrees of your polynomial you're supposed to have, right? In a similar way, I would imagine that it should be able to tell you okay, how many components are you supposed to divide into? Is that I guess you must have thought of this. Does that actually work?
The story is a little bit more nuanced in that minimum description length, whenever you're dealing with, say, some continuous variables, you may have to fix one of your continuous variables and say, for a given value of this continuous variable, how few can I get in these other variables?
Right.
And suppose in the case of an SAE, you might say, for a given mean squared error, or how low can I get my my L0, sorry, how low can I get basically the description of this set of activations, where that depends on how many things are active for a given data point, and how many features I've used in my sparse autoencoder dictionary. The same thing kind of applies in APD. You need to fix some of your variables. So the mean squared error is one of them. If you really want your mean squared error to be very, very low, you might need you might get to ablate fewer parameter components, because you'll just predictably increase the loss if you ablate things, even if your parameter components are perfect. But there are also some other continuous variables here. Even though we're trying to minimize the rank, we do rank is a non-differentiable quantity. What we are in fact getting to minimize is it's basically the sum of the singular values of the matrix. This is what we call in the paper the Schatten norm. That's just the name of the quantity. And so this is like a continuous approximation of the rank. If you minimize this basically if you minimize this, you minimize the rank. But it's not a perfect quantity. But this is our measure of simplicity, and we kind of have to say, for a given level of simplicity, how few active components do we get to have. So there's a lot of degrees of freedom that we have to hold constant, such that we can hold them constant and say, how well can I do in terms of minimum description length. But we basically want to get toward a method such that we we hold these things constant at a sufficiently low level that we don't have to really worry that we're introducing arbitrary choices.
Right. I mean, I think so. In terms of okay, you've got to balance against the loss. I had this impression that for a lot of these mean squared error losses, you could actually think of it as the likelihood of something and end up measuring it in bits. I don't know as much about, so it makes sense that you would have to think about singular values rather than literal rank, because like in the presence of any noise, like every matrix is full rank, right?
Yeah.
Yeah, I think I wonder if it's a thing. I wonder if it's going to come down to, so you are dealing, like one thing going on with description length type things is that like, you know, description length is inherently a discrete concept, right? Like how many bits are you using to describe a thing? Yeah. And if the thing is continuous, it's like, well, at what resolution do you want to describe it? And I think like this ends up being a hyperparameter, like a hyperparameter of MDL that like does, it seems like it's relevant. In this case, it seems like, you know, how many bits do you need to describe the stuff? Like if it's parameters, then like, you know, you can control that by saying, well, if I quantize my network with however many bits, how bad is that? Like, I don't know. Maybe I should, maybe this is one of these things where if I like sat down and tried to do it, I'd realize the issue, but it seems doable to me. It seems like there's possibly something here.
Yeah, I do agree that it feels like we should be able to at least find, you know, a satisfactory, you know, Preta frontier for minimum description length. I'm not sure we'll be able to get away from, you know, from that, you know, requiring that it just be a Preta frontier. I'm not sure there will be some sort of, you know, single optimal version of it, but at very least, I do think we can do better than the current algorithm.
Fair enough. So I think the thing I next want to talk about is basically the experiments you run in your paper. Yep. So in my recollection, in the main paper, there are like basically two experiments, or, you know, conceptually there are two types of experiments. So there's firstly this like toy models of superposition. Yep. And secondly, there's this I forgot what the short name of it. Sorry?
Compressed computation.
Compressed computation, yeah. So maybe, I mean, you spoke about it a little bit earlier, but first, can you like recap, what's how the toy model of superposition experiments are working?
Yeah, so some of the folks who are reading our paper and many listeners will be, you know, familiar with the model, but again, it's just this matrix that projects sparsely activating data down into some bottleneck space, and in that bottleneck space, features have to be represented in superposition such that there are more features than dimensions in this bottleneck space, and then the matrix has to up project them back to the original space of the original size of the number of data features, and then, you know, basically, so it's like an autoencoder setup, and because it gets to, I don't know, because it compresses these data set features down, it's kind of in some sense unintuitive that it can actually do this because it has fewer dimensions than features, but it can, because it has these, you know, like fewer dimensions, there will be some, you know, interference between features that are not orthogonal to each other in this bottleneck space. But the way it gets over this is that because it has ReLU activations following the up projection, it can kind of filter out some of these this interference noise, and, you know, do a reasonably good job at reconstructing the input data features. Now, one of the ways you might think about this network is that we have this matrix, and if one of the input data features is active, well, only say one row of the matrix is actually necessary. We can basically throw away the other rows. We can set them to 0 in cases where only this you know, one, let's call it, you know, input data feature 1 is active. And in particular, the row that we have to keep is, you know, the first row.
Yep.
So we can basically set the other rows to 0. And so there's some sense in which the rows of our toy model are like the ground truth mechanisms.
Right.
And because why are they the ground truth mechanisms? Well, they satisfy the properties that we wanted to that we're aiming to recover here. So we have, they all sum to the original network. That is, all the rows, whenever you set to 0, the other rows set, that basically sums to the original network.
Yep.
Because then looking at minimality, because the data set features are sparsely activating, there is like if you only activate the mechanism that corresponds to that data set feature and you don't activate other ones, well, this is going to be the shortest, the smallest number of mechanisms that you have to activate on this data point. So it's minimal, and they're simple in some sense in that single rows of this matrix, when you zero out all the other rows, are rank 1. They just correspond to the outer product of an indicator vector and the row itself. So they satisfy the what we want to call a ground truth mechanism, and this is the things that we're basically optimizing are randomly initialized parameter components to try to approximate. And so what we then find whenever we do this is that at least for a given set of hyperparameters, we are able to recover this set of ground truth features using APD.
Okay. And how, like, so in the paper, so one thing you mentioned is that so the original toy models of superposition, it like has a bunch of geometry and it draws some pictures, and that's partly like relying on the fact that it's there are like 5 inputs and 2 hidden units, and that's a setting where like it's just very small, and so things depend on a lot on hyperparameters. So you also look at a somewhat higher dimensional case where there's like 50 inputs and 10 hidden units or something. Is that right?
It's 40 and 10, yeah.
40 and 10, yeah. So my understanding is that you're pretty hyperparameter sensitive in this like really small setting. In the like 40 and 10 setting, how hard is it to get the hyperparameters right?
It's easier, but I still think it's pretty hard. But the 5 and 2 case is particularly challenging because optimizing in a 2-dimensional space is just it's something the gradient descent is not especially good at. I mean, it can do it. It's just that like moving vectors around each other can be kind of more difficult in 2-dimensional space versus in n-dimensional space, where they basically just get to move in any direction and not interfere with each other.
Right.
In 2-dimensional space, there's just much greater chance for interference.
Okay. And so, yeah, I guess I'm just especially drawn to this hyperparameter of how many components you have. Just, I don't know. Is it, for some reason, to me, it feels like the most juicy hyperparameter, even though, obviously, I guess, like, relative weighting of these objective terms and, all sorts of things are also important. If you get the number of, well, like in this case, you have a ground truth number of components.
Yeah.
If you get the number of components slightly wrong, like what happens? How bad does it go?
I can't recall like an exact story for what happens, but for some cases it will kind of learn a bunch of reasonable features, but then in some cases it will in some features will just not be learned. In other cases it will be just much more noisy and it'll fail to learn altogether. I can't give a good sense of like how sensitive it is to this hyperparameter. My colleague Dan will have a much more informed sense of like the how sensitive it is to twiddling this, but it's also hard to tell is it this hyperparameter that is the most sensitive thing versus others.
Right.
There's just because there's basically a bunch of different hyperparameters to get right here. It's hard to get really intuitive around any given one of them.
So okay, I eventually want to get to a question about like all of about these experiments in general. And so in order to get me there, can you tell me about the compressed computation setup and like what's going on there?
Yeah. So compressed computation is the name for a phenomenon that we observed in our experiments. We were initially trying to model two different things. One is a theoretically well-grounded phenomenon that is that my colleagues Lucius and Jake had talked about in a previous post of theirs, computation and superposition, where a network is basically learning to compute more functions than it has neurons. And there's also a related phenomenon that's more empirical, which is from the original toy model of superposition paper that they also called computation in superposition, which and then there's this third phenomenon that we've called compressed computation. Now, it may be the case that all of these are the same thing, but we are not yet confident enough to say that they are all exactly the same phenomenon. The reason is that we are not super confident. At least we're not at the time. We became a little bit more confident and have slightly updated against the update that the compressed computation is similar to these other forms of these other phenomena, computation and superposition. Which one I would not be able to answer.
Okay.
But like the overall, but it is nevertheless the case that all of these can be described as learning to compute more functions than you have neurons. It's just that there's a fair bit of wiggle room in the words when you put those words into maths.
Sure. And the basic, so with toy models of superposition, the basic intuition for why it was possible to, reconstruct more stuff than you had, hidden activation space dimensions was that like the stuff you had to reconstruct was like sparse. And so, you didn't have to do that many things at a time. Is that the same thing? Sorry, this is almost definitely the paper. In compressed computation, like, is the trick just like it doesn't have to compute all the things at the same time, or somehow it like actually really does compute all the things at the same time with like less space than you thought you would need?
This is the point in which we're uncertain. Basically, we are we are not super confident about how much this phenomenon depends on sparsity. Now, we're also just not super confident on how much the anthropic toy model of computation and superposition depends on sparsity. Now, we know in their example it does, but we don't, because we don't have access to the experiments. We don't know how much what was going on in the backgrounds of those figures. We just haven't got around to doing extensive experiments to actually figure that out. It wouldn't be too difficult. But in our case, we're basically quite uncertain as to how much our phenomenon depends on sparsity. My colleague Stefan has done some experiments in this direction. It's somewhat inconclusive for now. I think he's got a project ongoing on this that hopefully there'll be a write-up of soon. But long story short, it may or may not depend on sparsity, but I think for the purposes of the conversation, it may be reasonable to proceed as though it does.
Okay, so basically, the thing of compressed computation is like computing more functions than you have width of internal neurons, and it's sort of surprising that you'd be able to do it, but you can. And my understanding is that the particular functions you're trying to compute are ReLU functions of the inputs.
Yes.
And you might be like, ReLU networks, shouldn't they be able to do it? But the trick is like, the network narrows significantly.
Yeah.
And so what is the hope here? Like what should APD be able to do in this setting if it's working?
So in this setting, the ground truth mechanisms are supposed to be things where even though the data has, say, 100 input dimensions and the labels are 100 relos of that input data.
Yep.
The models have learned basically to compute 100 relos using only 50 relos in the model.
Yep.
And the idea here is that, well, if they're able to do this, they are in some sense, using they're distributing their computation over multiple relos such that they can nevertheless do this without interfering with other features whenever they're not active. So you're basically computing more functions than you have neurons because you're not always having to compute them all at the same time.
Right. And so this is just because if you have a negative input, then all you have to know is that its relu is 0, and you don't have to do that much computation to make sure you have the identity function.
Yes.
Yep.
And also, but in other cases where suppose you have two input features that are positive, and so you need to compute two relus. Well, if you have basically projected one of your input features to one set of hidden neurons, such that you can spread your your relu function over these multiple relus, and if they are like a different set of hidden relu neurons than the other feature, then you should be able to get make a good approximation of the relu of the input data, because the magnitude matters here. You don't really want if you use the same. Suppose there was some overlap in one of their neurons between these two input features. Well, they would double up, and that would contribute to. They would basically overshoot in the output. And so if you spread things out a little bit, such that they don't overlap very much, you should be able to compute things with some interference, but ultimately compute a bit more functions than you have neurons. But yeah, the cost is interference.
Gotcha. And so, yeah, just as long as you're distributing over the set of neurons. A thing that I just realized, the fact that you're going from 100 inputs to 50 wide, which is half of 100, is that just the same thing? Is that just for the same reason as numbers have a 50% chance of being positive and negative? And so on average, you only need to represent half of them?
I don't think the number 50 was especially important.
Okay.
I think we could have easily chosen something else. I think it was just I think it was somewhat arbitrary.
Okay, fair enough. All right, so I was asking what APD is meant to get, and what was the answer to that again?
Yeah. So thanks for reminding me. So I was trying to get a sense of what the ground truth features should be. And the ground truth, I said ground truth features. Ground truth
mechanisms.
Mechanisms. And these ground truth mechanisms should be things that distribute across multiple hidden neurons. So the input, you got this down projection matrix and then this up projection matrix. This is a rather, maybe think about it as an embedding matrix, then an MLP matrix, and then an embedding matrix, an MLP in matrix, an MLP out matrix, and then an embedding. So it's a residual architecture. And so you have this embedding matrix and this MLP in matrix, and whenever you multiply these two matrices together, you basically want to show that a given input dimension projects onto multiple hidden features. Multiple hidden neurons, and this is what one component should do, and those hidden neurons should then project back to that output feature that corresponds to the input feature that you care most about. And so you can basically do this for multiple multiple input and output features. you want because your input and output features are like sparsely activating, you want your parameter components to mostly only correspond to one of these input and output
Right.
computations. And so you want basically to have parameter components that line up strongly with these input and output components.
Right. So it seems like the thing is you don't like, maybe you don't know exactly like what the components should, like you don't exactly know which parameters should light up or whatever, but you do know like for each component that APD finds, it should reconstruct the ReLU of like exactly one input and like none of the rest of them. Is that basically
yes.
right?
Yeah, basically, yeah. Because in this case, we basically get to define what the minimal set of components is, because we get to choose a lot about the data distribution.
Okay, so I think the thing that I'm wondering about with both of these tests is, so I think of the kind of idea of APD as like, previously a bunch of people have been like trying to explain feature, representation of features. They've like looked at these neurons, they've said, what do these neurons represent? But you want to find the mechanisms, right?
Yeah.
Now, the thing that strikes me about both of these examples is they feel very representation-y to me. They're like, okay, we've got this sparsely activating input, and we've got this like low dimensional bottleneck space, and we want to say, we want to reconstruct these parameter vectors to tell us like how the bottleneck space, is able to reconstruct the inputs, each of component of the input. Or for ReLU, right? It's like, okay, somehow this thing like, like for each of these inputs, there should be like something that's like representing the ReLU of that input, and I just want to like divide into things that get the ReLU.
Yeah.
Like it seems to me that like networks could have a bunch of mechanisms that like don't necessarily do representing individual features or things, right?
Yeah.
Or potentially like representing things could involve like a bunch of mechanisms. Like for any given thing you represent, like maybe there are like 5 mechanisms that are necessary. So yeah, but basically I just had this thought reading this paper of like, it feels like the experiments are too representation-y and not mechanistic-y enough. What do you think of this anxiety that I'm feeling?
Yeah, I think that's reasonable. I do definitely I share this. There are a few toy models that we would be keen to see people work on. For instance, you might. Well, I'll also, just before I get into that, just say, yeah, I do think that there's like some sort of there's in some sense it's not a perfect duality between representation and mechanisms or computation, the kind of computation-y kind of point of view. There's nevertheless a relationship. It is therefore more a matter of perspective, like which one is most convenient to think about at a given point in time. Now, I do think that when designing these toy models, we wanted to get a method that works in a very simple setups where these representations do in fact correspond to the mechanisms, right? And this is a case where it's been easy to design networks where there's a ground truth that's easily accessible to us. We find it a little bit harder to design train networks where you could be somewhat sure of what the ground truth was, even though there are multiple computational steps that may be involved. Now, I think it's perfectly possible. We did have some cases where we handcrafted some models. There's an example of this in the appendix, but that had some pathologies. The gradients didn't work especially well on this because it was handcrafted, and so we did find it somewhat challenging. Now, there are some models that you could think of that may capture this notion a little bit more than the ones in the paper. One that's very similar to what is in the paper could be, consider a toy model of superposition model, where instead of just this down projection and then up projection, you have a down projection, and then, for example, an identity matrix in the middle, and then an up projection. Or you can replace this identity with some other a rotation, say. Now, like, what would you want APD to find here? Well, you don't really get to think about it in terms of representations anymore, because fine, you've like broken it up into these mechanisms in the input, in the down projection and in the up projection, but there's this bottleneck where you're doing something in the bottleneck. If it's an identity or a transfer or a rotation. Suppose it's a rotation. It's probably easier to think of that. You're basically having to use all ranks of that rotation in the middle at all for every given data point. You don't actually get to chunk it up. And so what you would want then is you'd want APD to find is parameter components that correspond to the things that we originally found for the simpler example here, where it's just the rows of the down projection matrix and the up projection matrix, but then also a component that corresponds to this rotation in the middle. Why? Because you're having to use this all ranks of this rotation for every data point. You always have to do it. You don't get to throw it away and reduce your minimality. You don't get to make it any simpler to reduce your simplicity. It's just always there. And so this is maybe a case where you do get to think about it in terms of computational steps rather than representations.
Yeah, I mean, I think that... Okay, actually, before I go further, just to pick up on a thing I said, so I believe this is in Appendix B1, you like hand designed these networks to compute these functions or whatever.
Yes.
How did you hand design the networks?
So I believe this was Jake and Lucius and Stefan. I may be misattributing there, but I've at least included all of them. One or the other may not have been involved. But they, I think, just thought about it really hard and then came up with it. I don't have a great, they're not super complicated. They're not super complicated networks. They just they have particular steps. They just have a little gate. And you for certain inputs, your gate is active, and on other inputs is not, and this lets you do subsequent computations on it. I could be it's been a little while since I've looked at it, but the basic principle is that it's not a complicated network.
Yeah, I guess so. My recollection is that it's like basically sinusoidal functions, and I guess if I had to, I could write down a network that like if you just divide it up into piecewise linears, right? For a wide network, you can figure out how to do it. It's just like kind of tricky.
This network gave us a lot of grief because the it's intuitively quite a simple network, but because we're using gradient-based attributions, it just didn't play nice with the method, even though to our naive selves, it intuitively felt like it should. But we eventually got it working. But it is demoted to the appendix.
Fair enough.
Punishment.
So you're talking about so you mentioned in this toy network where you have like kind of project down, do an operation in like down projected space, and then like unproject back up. Well, like this is ideally what APD should find. When you say it like that, it sounds like an easy enough experiment to run. Like, have you tried it?
I believe we at various points gave it a go. I think it just wasn't like top priority to get the paper out.
Fair enough.
It's very possible that we have got this working already, and I'm just forgetting. It's also very possible that we had tried it and couldn't get it working, or at least didn't want to invest the time to get it working, such as the sensitivity of the hyperparameters. But I would be keen to see a verification that it is at least possible for APD to find this. Intuitively, it feels like it ought to be able to, but just like to see it empirically.
Sure. I guess like other things that strike me as interesting to look into. Um, so so there are a few cases in the literature where people do really seem to have identified mechanisms within neural networks. Um, I guess the most famous one is like these induction heads, right? Where like induction, like as some people have pointed out, it's like it can be kind of a loose term. Like people can use it for a few things, but in at least some cases, people can just point to like, look, this attention head. If you pay attention to like this thing it's doing and this thing it's doing, I guess it's two attention heads, maybe, but like you could just tell a very clear story about how it's like looking for an initial thing and then like taking the thing after that, and then like this thing copies the thing after that into the output. So that's one example of a thing that feels very much like a mechanism and does not feel so like representational, Another example is group multiplication. These neural networks that are trained on group multiplication tables, they have to get the other ones. Like I think I guess I was like semi involved in a paper. I chatted with one of the people and like tried to make sure he was on track for things. Awesome. But there's this Wilson Wu paper that's basically together with Jacob Drury, an author I'm forgetting, Jason Gross, and basically they I think they end up with like a pretty good story of like how these networks learn group multiplication. Yeah. And they could basically tell you, right? They do this thing and then they transform. They do this thing and then they transform it in this way and then they get this output, and like it works because of this like weird group theory fact. Mm-hmm. Like I think there are a few more of these. I guess like for at least those examples, like do you think like can we get APD working on those? How hard would it be to like check if APD actually like works on these?
So it feels possible, certainly in toy models for the induction head. Indeed, it's like, it was one of the motivations for APD that I'd been working with various math scholars, Chris Mathwin, Keith Winrow, on Felix Biggs as well, on attention, decomposing, attention in neural networks, and it's basically just intuitively quite, it feels like you should be able to do this. Just add in an SAE here or transcoder there, and like you can kind of make some progress in this, but it just didn't feel conceptually very like satisfying. And it basically was one of the motivations for APD that, well, we really want a method where we don't have to like modify it such that if you have a slightly different architecture, like maybe it's a gated linear unit, or maybe it's a state space model. Ideally you wouldn't have to like adapt your interpretability methods to these. You should just be able to decompose, just apply the method that you have that works for all neural networks. That would be ideal. And so this was one of the motivations, like looking at attention and how it may actually distribute computations across heads or various other ways to distribute it. Now it feels possible then that we should be able to do this in toy models of, say, induction heads. It would be a somewhat more complicated model than APD has been used for thus far, but it does feel possible, and it's one of the things I'm excited about people trying. In the cases where say group multiplication or modular addition, it's very possible that if you did apply APD to these models, where you don't really get to, it feels possible that in these models, all mechanisms are active all the time, and therefore you just, APD just returns the original network. And if that's the case, this is a bullet I'm willing to bite on the method. Sometimes we just don't get to decompose things into more things than the original network. These are, after all, fairly special networks trained in quite different ways from the tasks that we really care about, such as language modeling. It's nevertheless something of a something to bear in mind when applying APD to models. It's not going to immediately tell you in cases where it may be a multidimensional feature, like how to understand the interactions within this this multidimensional multi-layer component. But at very least, what we wanted was a method that would, in cases where you could decompose it, where it actually succeeds in doing that.
Right. So sorry, the thing you said just inspired me to look at this paper. So this is so the paper is towards a unified and verified understanding of group operation networks. And the author I was forgetting was Louis Jabouri.
Okay.
So, sorry, Louis. I think, yeah. So there's this question: for group multiplications, are all of the things like active at once? I think. Okay, I think I'm not going to be able to figure it out quickly enough in time for this, but yeah, basically, like, I don't know. It does seem like an interesting question of like, can you get APD working in a setting where like I guess it's tricky because like it's a lot easier to have ground truth representations than ground truth mechanisms, especially if you know like, okay, I'm an autoencoder, or I'm doing like this known function of like each individual input. And I guess this sort of just relates to the fact that we understand like representation is just much easier for us to have good a priori theories of than computation, somewhat unfortunately.
I'm curious what you... Yeah, I'm just too APD brained at this point, but I'm curious where... Yeah, could you flesh that intuition out a bit more? I feel like what it means for, a hidden activation to represent one of the input features in the TMS case doesn't feel intuitively obvious to me. It's fine. It corresponds to one of the... There may be a direction in hidden activation space that corresponds to one of the input dimensions. It doesn't feel like more intuitive, that point of view, than say, this input feature activated that computation. I'm curious.
Oh yeah. I guess like all I'm saying is that like with toy models of superposition, right? The reason you can very confidently say like, okay, this like it feels like the reason you can very confidently say like this part is doing this thing is like in some sense that like all the neural network has to do is like it has to like put a bunch of information into this two-dimensional knapsack and be able to like get it out again, right? Like that's just everything the network's doing. And you can kind of say like, okay, well, I understand that it should be sensitive to all these things, and like I guess there are some things you can say about the computation there, but like for cases like compressed computation, like toy models of superposition, you can just say like, okay, look, I have these things, and I know this input should correspond to this output, right? Like that's just like definite ground truth because it's like basically what I'm training on.
Yeah.
Whereas like it's a lot harder to look at a network and say like, well, I know it should be doing this computation and I know it should be divided up into this way. Like that's...
Yeah, I think that's fair. Yeah.
And therefore like it's easier to like test against like, well, do I reconstruct this thing in toy model superposition where I like know what I'm supposed to reconstruct versus like, do I reconstruct this, way of doing things in like this, where like I don't, a priori you don't exactly know.
Yeah. I think that's fair. And I think this maybe is, part of the... This goes back to a little bit of what we were talking about at the start, where there is this... even though there may be multiple equivalent ways to describe the computations going on in the network, we really just have to, be opinionated about like what constitutes a good explanation. And faithfulness to the network, minimality, and simplicity are just the ones that we think are a reasonable set of properties for an explanation to have.
Fair enough. So, okay, I think I'm going to transition into just more asking miscellaneous questions mode.
Yeah,
that's less grouped by theme. I think the first thing I want to talk about is that at one point in your paper, you say that like, so why are we doing APD on like these small networks and not on like, llama, whatever, however many billion models you can get these days. And the answer is that it's like kind of expensive to run APD. How, like concretely, how expensive is it to actually run?
So I like the version that we've come up with here is, we didn't aim for efficiency. We didn't aim for, some of the obvious things that you might try to get a method that works more efficiently than ours. The reason being that we wanted something where on theoretical grounds we could be, somewhat satisfied with it and satisfied with it working. And then after that we can, move to things that are more efficient. But so for the current method, what we have here is, for a start, we've got like, let's call it, the letter C components. That's, how many, we've got C components.
Yep.
And each of these require as much memory as the original model, right?
Yep.
Now that's, already, a multiple of the expensiveness of the original model just to do one forward pass. We also have, the first forward pass, the first backward pass, the second forward pass and the second backward pass. So we're having to, during one training update, we have, these four steps.
Yep.
So you're already like, it's already a multiple of just, a given forward pass and backward pass that might be required to train an original model. But I guess, different goals with each of these steps.
And how, like, so I don't know, maybe the answer to this is just it's another hyperparameter and you've got to fiddle with it. But like, so there's a number of hyperparameters there's a number of components that you want to end up being active, right? Like this K that you talk about. And then there's just like a total number of components that you have to have in order to like run the method at all. Like, is there something to say about like, oh, it turns out you need like 5 times as many total components as you want components active in any single run? Or is it just like kind of a mess?
Well, some people will be familiar with training sparse autoencoders, and in some cases you start with more than you expect to. You start with more features than you expect to need. The reason being that during training some might die, and there's various tricks that people have invented to stop them dying, reinitialization, and so on. The same is true in APD. Some of these parameter components will, in some sense, die, and depending on the type of model, and you will, want, therefore, to, in general, you'll want to train with a little bit more than the total number of ground truth mechanisms, just so that if in the off chance that some do die, you still nevertheless have enough to learn all of the ground truth mechanisms.
Okay, but it sounds like you're thinking that it has to be like, more like a factor of 2 than a factor of like 100 or something.
That would be my expectation. I don't think there's going to be, a ground truth answer to that. But yeah, I think, it wouldn't be. I don't see any reason why it would need to be, many multiples higher.
Okay. So yeah, I guess if you're thinking about the expense of this, it seems like, okay, you have this like constant blow up of like, you've got to do like 2 forward passes and 2 backward passes on each like gradient step. And also you've got to keep on, having like, these C copies of the network, around at all times. And then there's this question of like how many steps it takes to actually train APD, which presumably is just an empirical thing that like, is not super well understood. I think like, I guess one question I have is, if I remember correctly, there's some part of your paper where you mentioned that like naively APD might take order of n squared time to run. Do I remember that correctly?
Yeah, I think this is like a pessimistic upper bound on like the expensiveness, but I think there's plenty of reasons to expect it to be lower than this. But I would need to revisit the sentence to be 100% sure what we're actually talking about. Yeah,
fair enough.
There is a sentence that does have talks about the scaling and mentions so n squared. Yeah.
Okay. So okay, the next thing that just came across my mind that I wanted to ask is when you're training for a minimality, right? So on each input, you like, you run it forward, you get like you do attribution to get the K most active components. And and then you like drop all the other components,
Yeah.
and then like have some training step to make the k most active components like reconstruct the behavior better on that.
Yeah.
I'm kind of surprised. It seems like one thing you could imagine doing is also having it be like training the ones that you dropped to be less relevant on that input than they actually are. I'm wondering if like you tried this and it didn't work, or if this is just like less of an obvious idea than it feels like to me.
Yeah, I guess so. Like concretely, what you might consider doing in that case would be, you run it. You might have a third forward pass where you only run it with. I guess I don't know. It may be hard. I haven't thought about this enough, but it may be hard to distinguish between the influences of like. I don't know. It feels on the face of it, it feels like something that could be useful to implement if it's possible to implement. It It does feel possible for sure. I don't recall us trying it though. The things that we did try were the top K, and then we also tried like an LP sparsity version where you penalize everything for being attributed. You penalize everything for having some causal influence over the output, but you penalize the things that were most causally attributed proportionally less than the things that were had some small influence. And this is kind of doing that where you're like but it's not equivalent, but it feels possible to do that. I'd be curious if it could be done.
Gotcha. So I think at this point I'm interested in what follow-up work you think is important to do on APD. Either they you think is important to do, or if enterprising listeners like maybe want to pick up some of the slack.
Yeah. So I've mentioned a few of the things that I'd be keen to see already. So non-exhaustively attention. I'd be curious to see if it can decompose attention in a sensible way. There's various other things. However, the main thing right now is figuring out whether or not we can make it less sensitive to hyperparameters and more scalable. Basically, these are the two. Robustness and scalability are the main things that we're keen to solve. Just because it will open up. Whenever we do, investigate these other things like attention, distributor representations across attention, that will be less painful to do. And also you can do this in larger, more interesting models. So the main thing is scalability and hyperparameter sensitivity or robustness. So if those being the two main things, suppose we solve those, I would be keen to see attention, keen to see other types of architecture decomposed here. There's also a few other phenomena that you might be curious to apply APD to. For instance, the phenomena of memorization, right? There's this. You might imagine that memorization, whenever APD successfully decomposes the network into memorized data points versus generalizing data points. Memorized, there may be one parameter component that corresponds to one memorized data point, and one parameter component that corresponds to a generalizing computation within the network. It may therefore be a nice place to distinguish between these two kind of computational regimes of memorization and generalization. So I'd be keen to see APD applied to that. I mentioned some of the more theoretical things that you might want to look into, such as privileging layers, or more implementationally figuring out whether or not we can get rid of having to do a top K setup where you have to choose K. Then yeah, there's basically there's a bunch of fairly disparate directions, all of which I'm super keen to see done. I think like our main priorities now are just creating a method that makes those other things a bit easier. Those are non-exhaustively though. There's a more more exhaustive list, I think, in the paper.
Makes sense. I guess so a couple things that seemed interesting to me that I'm curious if you have comments on. So one thing that I guess somewhat inspired by our discussion about doing APD to a car, right? It seems like APD is a method that sort of is sensitive to the input distribution that you do training to. And I think there's this interpretability illusions paper that says, sometimes you might think that you have a rich enough input distribution, but you don't actually. I think just how sensitive you are to this input distribution, how right you have to get it. I think I don't know, that's something that I don't know if you've had much preliminary exploration into, but it does seem pretty relevant.
It seems relevant. I think this is in some senses unavoidable, just because I want to decompose neural networks. What does that mean? Well, it means to decompose what these networks are doing. What they're doing depends on the input distribution, and just simply with a different distribution, natural or unnatural, it just will kind of lead to different things. I do think that when we get to more scalable versions of this method, this will become even more important. You ideally want to have a method where suppose you're decomposing llama 3 or whatever, if you've got a scalable scalable method, and you present it with one, you train it using the training distribution of llama. But then you also train it with the training distribution of llama permuted. You ideally want to, end up with the same thing. Similarly for, a large enough subset, and then, more adversarial subsets. It will be the case that, for a sufficient level of adversity, it will break. I think this maybe, emphasizes the importance of just doing interpretability on as large a distribution as you possibly can, and which stands in contrast from some of the interpretability that's happened in the past. I like to call this just using the big data approach, where you're basically just doing you're finding structure first and then asking questions later. It just feels it's kind of borrowing from regions of science or areas of science where there's just a lot going on, and you kind of want to leverage computation first to actually narrow down what questions you really ought to be asking. In this, the application here in interpretability would be you want to let the computationally informed let computational methods do the work first, and then you figure out what does this component mean, rather than presupposing some kind of your own ideas of what the components ought to be, and then studying those in more detail. This is the kind of approach that I think ABD intends to leverage, this big data approach, and I think that's somewhat unavoidable in interpretability, that I don't know can tell you things that you weren't looking for in the first place.
Fair enough. I guess so another thing that struck my eye in the paper is, so there's a section that is basically I think of this section of the paper as basically saying why SAEs are bad and rubbish. And one thing that is mentioned is there's this feature geometry in SAEs, right? Sort of like the day of the week thing, where they're they're in a circle Monday, Tuesday, Wednesday. And I think there's some line that says, that the fact that there is this geometry is not, as maybe Jake Mendel has written about this, but this is not, purely explained by this like linear representation hypothesis. We need like to understand mechanisms to get us there. How soon until APD tells us what's going on with SAE feature geometry or feature geometry in general?
Yeah, so Jake's post was, if I'm recalling the title correctly, feature geometry is outside the superposition hypothesis.
Right.
And feature geometry is this idea where it's a reasonably it's older than the mechanistic interpretability community. This idea was present in neuroscientific literature a bit before, but the idea here is that suppose you've got a neural network and you train an SAE on the activations, and you look at the features that you end up with. These features tend to correspond to certain things. This was the whole point of training SAEs, to identify interpretable individual components. But whenever you start comparing the directions of these features relative to each other, you'll notice that, well, if I look at the Einstein feature, well, it happens to share it kind of has some non-zero, rather, if I look at the Einstein direction, the Munich direction, the
Lederhosen.
I don't know, Lederhosen direction, and so on, you'll find that all of these kind of point in somewhat similar directions. There's a kind of latent semanticity to them. There's something underneath these features. These features were supposed to, correspond to the computational units of neural networks. And now what this like feature geometry is indicating is that there's like an underlying computational structure that organizes these features relative to each other, which is like, in my opinion, something of a, this doesn't bode well if you considered SAE features to be fundamental units of computation, because you shouldn't be able to identify these like latent variables that are shared across multiple features. And the hope, like what's giving the structure? What's giving the structure? The relative, what is giving the geometry to these features? Well, like the hypothesis here is that suppose you've got these features pointing. You have the Einstein feature, and you've also got these other Lederhosen, this Lederhosen feature, and so on. Well, these all get the German computation done to them. They're all pointing in this direction because like somewhere down the line in the network, the network needs to do the German computation to them. And just apply some specific transformation or some set of transformations that all correspond to the Germanness of a thing. And you can imagine other cases for animal features. Why do all the animals like point in similar directions? Well, it needs to, the network needs to do animal related computations to them. Now you could go further. Why do all the furry animals like point in similar directions? Well, because there needs to be furry computations done to them. The hope here is that if you, instead of studying the features and trying to use that as a lens to understand the network, study the computations, and that will like inform why the geometry is the way it is, because you get to look at the computations that get done to it, which is presumably why the network is structuring them in this way. Now you don't necessarily, it's very possible that you just kick the can down the road there. You may find that if you decompose your computations into very simple computational units, well, you might find that there's some relationship between your computational units in terms of geometry, but it nevertheless feels like you've done better than the SAE case, basically.
Right.
I'm not saying it's not obviously totally solved the problem.
Yeah. So how long until APD explains all this?
Well, we first need to get a either you would need a toy model of feature geometry, such that it's a small enough model that you can apply APD to it, and that toy model would need to be convincing, such that it people can say that it probably applies to larger models. But absent a convincing toy model, you would need to be able to scale this such that you can apply it to larger models. I can't say for certain, when we'll have a scalable method. It's something we're currently working on. We're very keen for other folks to work on as well. I would be speculating irresponsibly to say when we'll have a working method for that. But I would hope that like anywhere between like 3 months and 3 years.
Okay.
That's the kind of uncertainty. Yeah,
but I guess it illustrates the importance of just robustifying this thing to make it easier to run on bigger instances.
Yeah.
So I guess the last question that I want to ask is what's the end game of APD? Like is the hope that I run it on the underlying model from of O3 or whatever, and then I just understand the all the things it's thinking about at any given point. How should I think about where is this going? What's it actually going to get me in the case of these big chain of thought funky networks?
Yeah, it's an important question to ask. I think the way I see this kind of work, and the way I see the similar work that came before, such as SAEs or transcoders or things like this, the point is to break up networks into as simple components as you can, such that whenever you try to understand larger facts about the network, you've got some solid ground to stand on. You can say, well, I got this set of components. If I understand, if I were invested, I could, in theory, just understand everything with this very large number of components. Now, do I really think that mechinterp is going to let us understand everything? Well, probably not as humans. But I do think that it will give us solid ground to stand on whenever we want to understand particular phenomena. Now, if I want to understand, say, the deception, mechanisms within e.g. O3 or any other model, well, where do I go looking for them? Well, currently we look at behaviors. One thing that you might be able to do is look at transcoder kind of approaches, but because transcoders and other activation-based methods are primarily looking at activations, they're not necessarily giving you the things that are doing the generalization, such that you are, I think you can be less confident that you're understanding how the network would behave in a more general sense. And by looking at the objects that are doing the generalization, by looking at the parts of the parameters that are actually doing the thing, you might be able to make more robust claims.
So I think that's I think it's fair enough to say look at very specific things. I guess there's also some world in which once you're able to have these good building blocks, you can do automated interpretability of everything, if you need to.
For sure, yeah. I mean, I guess I'm leaving that implicit. Yeah, the ultimate aim would be that you can automate the process by which you would understand parts of the network, such that you can understand broader swathes of it. And yeah, ideally, you have given yourself a solid enough ground to stand on that. Whenever you do this, fewer things will slip through the cracks.
Sure. I guess one thing that strikes me as interesting about these reasoning models in particular, I think that, and sorry, this might be a bit, this might be kind of far afield, but I think a lot of interpretability work has been focused on understanding single forward passes.
Mm-hmm.
What's the in vision, especially for classification models, right? The early stuff was done on vision classification, where yep. Of course, you just want to find the curve detectors or whatever.
Yeah.
And for SAEs, you're which things are being represented. One thing that I think reasoning models bring to light is, in some sense, the relevant mechanisms should be thought of as or it seems to me in some sense the relevant mechanisms should be thought of as distributed across forward passes, right? You do a forward pass, you write a thing in your chain of thought, then you like do another forward pass, you write another thing in your chain of thought. And in some sense, like the real mechanism is like, a bunch of these end-to-end copies of this network. And I wonder, like, this might be too speculative to ask about, but like where do we go in that setting? Like do you think it still makes sense to like focus so much on like understanding these individual forward passes versus like the whole web of computation?
I think it probably does. The reason being, what methods might we, what alternatives might we aim for if we wanted to, instead, just to ensure ensure that in these kind of more distributed settings where computations are spread across, a whole chain of thought. Well, what might we do in that case? We really care about, we care about the faithfulness of the chain of thought. So in the case where we care about the faithfulness, we want some way to measure like how faithful the chain of thought actually is being. And mechinterp does give you some, measure of, if you can understand, a given forward pass and, maybe even a small chain, it should give you like firmer ground to stand on whenever you make claims about, this method that I developed that improves the faithfulness of the chain of thought. Like, I don't know how you can make such statements without actually having, some way to measure the faithfulness of the chain of thought. And that's maybe, one way that mechinterp may be able to help in that regime. That's just kind of, I don't know, the one thing that comes to mind.
So wrapping up, I want to check, is there anything that I haven't yet asked you that you think I should have?
I think one of the things that I find, I don't know, most satisfying maybe about thinking about interpretability in parameter space is that many of the notions that we had going into interpretability become a little less confusing. So one of the main examples that I have in mind here is just this idea of a feature. People, have used this notion of a feature in a very intuitive sense and struggled for a long time, to actually nail it down. What is a feature? What are we really talking about here? It kind of, evaded formalism in some sense. And I think one of the things that I find most satisfying then about interpretability in primary space is that it gives you some foundation on which to base this notion. In particular, the thing that we might call a feature of a network is something that uses one parameter component. For instance, what does it mean to say that a model has a feature of a cat inside it? Well, you can perhaps equivalently say that this model does cat computations to it's got a cat classifier computation, or it's got a cat recognition computation. This is what I mean. There's a kind of duality between. It's not an exact duality by any means, but it helps provide a sense in which features mean something specific. In particular, it means there's whenever you break up a network into faithful, minimal, and simple components, these components, these mechanisms, are what you might reasonably call in some cases you can call them a feature. In other cases, it's more natural to think about them in terms of this is a step in the algorithm. This is a computation that the network is doing. And I think that in that sense, it's a bit more general than thinking about things in terms of features.
Fair enough. Well, I guess to finally wrap up, if people listen to this and they're interested in following your research, how should they do that?
Yeah, I post most of my things. I post them on Twitter, and I also post on the alignment forum as well. you can just follow me on Twitter and check out me on the alignment forum.
And so links to those will be in the description. But for those who don't want to open the description, are you just Lee Sharkey on Twitter in the alignment forum?
I think I am Lee D. Sharkey on Twitter, at least in my Twitter handle, but I should just be Lee Sharkey and findable by that. And Lee Sharkey on alignment forum.
All right. Thanks very much for coming here. We've been recording for a while, and you've been quite generous with your time. So thank you very much.
No, thank you, Daniel. It's been great. I've had an awesome time. Cheers.
This episode is edited by Kate Brunotz, and Amador Nace helped with transcription. The opening and closing themes are by Jack Garrett. The episode was recorded at FAR Labs. Financial support for the episode was provided by the Long-Term Future Fund, along with patrons such as Alexei Malafeev. To read a transcript, you can visit axrp.net. You can also become a patron at patreon.com/axrpodcast or give a one-off donation at ko-fi.com/axrpodcast. That's ko-fi.com/axrpodcast. Finally, you can leave your thoughts on this episode at axrp.fyi.